Well, good morning, everyone. This is Jeff Eisenman, and I'll be speaking today. This is basically a 2-minute warning for everybody to kind of get set. We're going to wait a couple minutes to let everybody come in, and then we're going to get started right at about 10 o'clock. So stay tuned. Good morning, everyone. This is Jeff Eisenman with Maverick Applied Science, and we're going to get started with today's webinar. So thank you for attending. Today, we're going to talk about non-metallic piping and chemical processing, lessons learned from case history. So we're going to be sharing some of our experiences and observations over the years on non-metallic piping and chemical processing applications. So let's go ahead and get started. All right, there we go. A little slow to respond here. Okay, as a general outline, we're going to talk about chemical process industry applications that are typical that we see. We're going to talk about piping materials and options, as well as piping construction. We always like to talk about our project execution plan, kind of what makes it work. And then we're going to be kind of sprinkling lessons learned through all of this. So it's not going to be just at the end, but we'll be talking about different lessons learned and observations throughout. and then we'll kind of try to tie it all up in the end. All right, where we use non-metallics principally is where we have corrosive chemistries, where we see corrosive applications. So, you know, to a great extent, these are some typical applications that we see, and you know, caustic soda, chlorine applications. We might see those in chloralkali, also chlorine dioxide, and pulp and paper. We see quite a bit as well. Hot brine, we see in a number of applications. Hydrochloric acid, sulfuric acid, and then sodium hypochlorite, commonly known as bleach, are all very common corrosive applications where FRP and non-metallics are a natural material for dealing with these. Many of these would challenge most of your metals, or many of your metals, particularly steel and stainless. You'd either have to go to a very high alloy if that was available. But in the chemical process industry, we see the non-metallics really handling these materials very well. So when we talk about non-metallic materials, and what we're going to kind of touch on today is thermoplastics. We're going to talk about lined steel piping, FRP, and dual laminates, and these are kind of the principal ones that we're going to talk about now. Now let's drill down a little bit. So when we talk about thermoplastics, we're talking about straight thermoplastic piping. So you know, generally this is grouped into three categories. Your vinyls, that'll be like PVC, for example. Polyolefins might be like HDPE, and then fluoropolymers. We're going to get into each of these more later. And then there's line piping, and what you see here pictured is carbon steel piping. With this particular one has a PTFE lining. So when we're talking about line piping, you know, generally that's kind of the scope of the piping material. If you look at the ASME standards, rubber line piping would also be considered a non-metallic in that way as well. Although for the most part, the standards treat rubber line piping under the standard steel rules, with the exception of dealing with the linings and things like that, which would be kind of separated out in the non-metallic section, like in B31.3, for example, Chapter 7. And then next, we're going to talk about FRP. So this is basically a thermoset resin. Could be a vinyl ester, polyester, epoxy resin with glass reinforcements, carbon fiber reinforcements, something of that nature. So when we're talking about FRP, so this is an example of a typical FRP piping. Generally, you have three components of the piping. You have the innermost layers is what we call the liner, or the corrosion barrier. This will be generally built, constructed of some one or more bales, followed by a number of layers of chopped strand glass. Generally something around 70–75% resin saturation in that layer. This is the main corrosion resistant component of the pipe. And then around that you have the structural shell. And these structural layers are basically designed to handle the pressure, the vacuum conditions, the structural spanning, all of the mechanical requirements for the piping system. And then finally, you have the exterior layer, and this could generally be could it be anything from a simple gel coat to might be, say, a bale and a mat. Generally, this would be for exterior weathering, exposure to outside chemical you know, vapors and things like that. One pipe dripping on another pipe. Largely, the biggest concern that we see is largely from weathering. So we're talking about the sun beating down on it, the rain beating down on it, and generally it's a direct wear issue is probably the biggest concern that we see with piping. On the exterior layers, generally people ask us because we see fiber bloom occur over a number of years, and generally we say that the pipe, if it were steel, we might want to see it repainted every 10 years or something like that. And with FRP, kind of that same thought process, where it's maybe 10 or 12 years, you might want to recoat that outside and put a fresh paint coat on it. But structurally, the pipe is still very sound, and there shouldn't be a concern there when we see fiber bloom on the outside. So the structural layers, one thing I wanted to talk about was basically it's where steel is a OD controlled pipe. So the OD always stays the same as you go from Schedule 40 to Schedule 80. Basically, the pipe gets thicker and the hole gets smaller in the middle, but the OD never changes. With FRP, it's just the opposite, where we have a fixed ID. So as we increase in pressure, the wall gets thicker and the OD changes. So this is where the right pipe supports are important. And largely, depending on the pressure rating, you'll see that's where we get into more custom applications, where say drain piping might be only 25 psi, where full scale pressure piping be 150 psi, and there'll be completely different OD, so you have to match the supports for that. So to get into the corrosion barrier a little bit more, so the corrosion barrier depends on the chemical contents that you're handling, which goes down into basically the size of the molecules, as well as the temperature that you're operating at. Higher the temperature, usually it's a more demanding application, so you need to select the resins based on that. Where we see chemicals that are more aggressive, chemicals that tend to have, say, small molecules, like, say, chlorine, for example, they have high permeation rates. So when we see that, or say like hydrochloric acid has a very small molecule also. So where we see greater permeation, that means that we need to design the corrosion barrier so we have basically a thicker corrosion barrier. So a standard corrosion barrier might be 100 mils for hydrochloric acid. We might want to go to 200 mils, so that we basically we don't want the permeation to go all the way through the corrosion barrier and get to the structural work and start to attack the structural integrity of the pipe. So we want the corrosion barrier to do its job and basically protect the structural cage of the pipe. So to continue on and discussing the corrosion barrier, so generally the corrosion barriers start with the surfacing veil, which may be sea glass. There's also an ECR veil, which looks very similar to the sea glass. There's a nexus veil, which you see pictured here in the second image. And then you see carbon veil, which from close up, it looks very similar to the sea glass, but obviously carbon is a black fiber. So so this is kind of an example of what it looks like. Generally, what we find is for acid service, sea glass is generally the best option. A few years back, ECR came in, and really it's been out for probably over 20 years, but really it's just come into I guess mainstream use probably in the last 10. And ECR veils are also a good option. Looking at the data provided from the glass companies, we find that sea glass is still got better resistance than ECR, although ECR is acceptable for those applications. And then we see Nexus veils typically used for base chemistries. So things like salts and caustic and things like that. Alkali type of chemistries, with the exception of bleach, which I'm sure if somebody from Ineos was on the line, they could probably go into that for an hour or two. But bleach tends to work. We see CC glass veils tend to work the best for that. And then carbon veils are something that's I guess beginning to come into use more. Carbon bales, we find where if we're seeing a very aggressive acid attack, we might go to a carbon bale, like say with HCl. We find that carbon works much better than even sea glass for that. It is a little bit more expensive, but for the amount of material you're putting in, it's not substantial. And then also where we see that, say we're having a lot of cycling going on, or if it were a vessel, if it's a very dynamic process vessel where it has cycling or a lot of mechanical flexing, maybe it's agitated or something like that, or we need a little bit more resilience to maintain the integrity of the corrosion barrier, we might go to a carbon bale as well. So kind of looking at the materials from a broad view, we find that FRP is generally stronger and more durable than thermoplastics, has higher mechanical properties, so we can get better spans. Thermoplastics tend to break down kind of like a dry rot almost. They get brittle when they're out in an outside environment where you have the sun and rain beating on it all the time. It tends to lose its resilience and gets brittle, and we see brittle failures for a lot of outside piping over time. I mentioned better spans. Obviously, the steel lined piping, where you're going to see the best spans, and sometimes that might be the reason why they use that. FRP is kind of, or dual laminate would be the FRP structure, is going to kind of be the middle ground for that. And then the FRP would also have an advantage because it's got a single integrated material. It's not it's not composed of two different materials like a lined steel, which has a loose lining, or a dual laminate, which has a bonded lining. So anytime when you're tying in a thermoplastic to an FRP or with steel, you just have more processes, more things to deal with and take care of. So there's more complications there. So the FRP, being an integrated material, kind of has a little bit, offers, I guess, simplicity. So, the less things to screw up. So that's why we would kind of lean to FRP as kind of the first choice for a chemical service there. And then also you don't have, we see creep concerns with line products as well, as well as thermoplastics. We see that, and I had mentioned the UV degradation. Cost is typically that's always one of the things that we measure, and to a great extent this depends on the materials. The bottom line of the thermoplastics, like say HDPE or PVC, is probably cheaper than FRP. Then when you get into the line piping, again, you're having more complicated processes or dual laminates. So those costs tend to go up significantly once you start putting say a Teflon line steel or something like that into a process. So now let's move on and talk about dual laminates a little bit. So dual laminates, I kind of mentioned, you can kind of see the images here. So dual laminates are basically composed of a thermoplastic lining that's directly bonded to an FRP structure. So you have all the mechanicals and strength properties of the FRP, but you would go to a dual laminate when, say, the FRP wouldn't handle maybe the surface directly, or maybe the surface is a higher temperature than typical FRP applications would be, say something over 200 degrees Fahrenheit or a little bit higher than that. You might look to a dual laminate versus just a straight FRP. So that's where we're getting into those, or maybe higher concentrations of chemicals, and those higher temperatures might be a reason we might choose to go to a dual laminate versus straight FRP or some of the other options. One thing I wanted to mention with respect to the lined piping is that whether with the line piping as well as the dual laminate, you have the thermoplastic lining, but one unique thing to thermoplastics is they do permeate, and the permeation doesn't stop at, depending on over time, depending on the thickness and the chemistry, And what lining it is, the chemical contents will sooner or later permeate through it, and then it gets to the structural cage, whether it be steel or whether it be FRP, and then at that point, really it's attacking the structure. And if you have something where you have say a lined steel application, well, once you get to the steel is going to go pretty quickly. So one of the things that the dual laminates does is it gives you a little bit more extended life and gives you an opportunity to actually reinforce those if you have sensitive points or say you have a leak or something like that. You can still reinforce from the outside and kind of buy some time until you can get it replaced, or you can just extend the life, to with I guess a limited repair. So drilling down on the thermoplastic linings, here's a slide kind of showing a variety of them, from the bottom being PVC and also being the cheapest, all the way up you see polyethylene, polypropylene, that's your polyolefins. And then above that, you see your fluoropolymers, PVDF, ECTFE, FEP, PFA are typical for your dual laminates. And then PTFE would be a lining that we see quite a bit with our lined steel as well. Generally speaking, if for rough ballparks, most of your linings are going to be something around 3 millimeters to 4 millimeters is pretty typical. They could get a little bit thicker if you go to some heavy wall CPVC or something like that, but that's pretty typical of thicknesses. And roughly, if you're looking at PVC to CPVC, we're talking, say, $8, a lineal foot or something like that for a lining, where you get up to like PVDF might be $25, $30, and then you go up to like FEP, maybe you're approaching like $50. So, and that's just kind of throwing a general ballpark of order of magnitude and the differences. But they all kind of have their place. The PVC or polypropylene don't work for everything, so there are places where service life is more important, so you kind of go up the ladder in the material choices as need be. One thing that I wanted to mention is when we look at thermoplastic linings, we're looking at the corrosion resistance based on the chemistry, what's the percent concentration, as well as what's the operating temperature range that's in. When you look at your materials like, say, PVC, CPVC, polyethylene, or let's just say PVC and polyethylene, polypropylene, you're pretty much talking about up to 160, 180 degrees Fahrenheit is really the ideal operating range. If you go beyond that, they may be suitable. Some will say up to 200 degrees Fahrenheit, but really, once you get above that range, you're going to diminish the service life substantially. CPVC is very much in that same way. Something when you get above around the 180 degrees to 190, that's really where it is going to be ideal. We see CPVC in a lot of process vessel applications, for example, where it's might be operating at 160 or something like that. When we get above that and we're approaching that 200 degree Fahrenheit, 100 degree C range, then we're going into the fluoropolymers, and pretty much as you go up the scale, we do see that you can go with elevated temperatures as well. When we're looking at thermoplastics, also I should mention that it's not just about chemical resistance, it's also about permeation. So all of these polymers are a little bit different. Some of them are harder, like CPVC is a very, very hard polymer. And you look at like ECTFE is also another one that's very hard. But yet you look at like a PFA or FEP is a fluoropolymer on the high end, but it's also not as hard and more porous than what we might see the some of the other materials. So we also want to look at permeation based on that specific chemistry as well. So when we're evaluating linings or even just direct thermoplastics, we want to consider our chemical resistance under the operating conditions, as well as the permeation for that specific material in that chemistry. All right, so something that we need to talk about is thermal expansion. So here's a general chart, and if you look all the way to the right, you see 316 stainless steel, carbon steel is next to that. Then you see hand layup FRP. You'll notice right away that hand layup FRP, and you see the units here are micro inch per inch degree Fahrenheit. So, but order of magnitude, you see FRP is at 180 degrees Fahrenheit is about 3 times the thermal expansion of carbon steel. So this is substantial. So it's basically in normal operating conditions, it's acting and growing like a steam system would at say 300 or 400 degrees Fahrenheit. And then if you look at further to the left at CPVC, it's again twice the thermal expansion as FRP. And then you look at like HDPE as 5 times. So the thermoplastics expand and contract substantially more than FRP. The dual laminates, generally the FRP will constrain them enough to where we don't see a substantial difference in thermal expansion for dual laminates, regardless of the liner. Obviously, the key is that it has to be properly bonded. But when you see, I'm sure many of you have seen like HDPE pipe that might be a drain pipe draining from one pond to the next, just laying on the ground, and in the morning it's a straight line going down the ditch, and you go at lunchtime and you look at it, and you'll see it looks like a snake in the ditch, and it's about to crawl out the ditch because it's expanded so much. That's a thermal expansion just from the radiant sun just beating down on it and heating up that line throughout the day. So that kind of gives you an idea of what we see in the thermoplastics. So because of this, in the last few years, particularly the thermoplastics, like say HDPE or PVC or some of the others, are being analyzed more and more because they're going into more demanding chemical processes. So, they need to be scrutinized more to assure that they're going to perform as expected. So we're seeing these systems being analyzed with greater detail, even with formal pipe stress analysis programs. So the project execution plan. So this is a very general project execution plan, and what I mean by that is that pretty much it applies to all projects and all materials, so it's not specific to FRP. The fundamental components are you want to have, basically comprehensive and current specifications. You want to have detailed engineering. You want to have, basically reliable manufacturing partners that are qualified for those specific products. And then basically you want to have in-process QC throughout the manufacturing process, and then throughout installation as well. So what we see is challenged with our non-metallic systems is when this plan doesn't get executed in completion and detail. And what I mean by that is, say we have good specs, but say maybe somebody chooses not to do a pipe stress analysis on an FRP or a dual laminate or even thermoplastics. We've analyzed HDPE systems for duct that have been higher temperature, say 160 degrees or something like that, and seen substantial thermal expansion to the point of, if it didn't have the right supports, you were at risk of failure. So you always want to make sure that basically every part of the process is followed through, and you don't take it for granted. You don't assume it's taken care of. You need to have checks and balances at every stage of the project. So now we're going to get into a few more lessons learned here and talk about, selecting vendors. Generally, what we have found in pretty much all cases, most manufacturers do one thing really well, maybe a couple things, but most manufacturers, when it comes to your non-metallics, they're either tank manufacturers or they're pipe manufacturers. There's very few that do both well. Just because it's FRP or just because it's dual laminates doesn't mean that they do tanks and pipe equally well. When you walk into their shops, you'll see very quickly that the shop is set up for doing tanks where you need lots of space and you need lots of manufacturing space for attaching heads and bottoms and nozzles and those sort of things, or they'll be set up for pipe where they're going to have fixed tables where they can jig up a pipe and level it out, and they're going to have dedicated stations for manufacturing T's and elbows and flanges and things like that. You're going to see very quickly that they're efficient at one or the other. So you'll want to know who you want to go to for pipe and who you want to go to for tanks. When we get into the materials, some materials are very unique as well and take a certain level of experience and skills, and furan is one of those where it's not your typical vinyl ester or polyester resin, and it has its unique behaviors and treatments, and there's only a few manufacturers who actually do furan well. So you want to, if you have a furan project, you want to know who does that. And similarly with the thermoplastic linings, generally when we look at dual laminate shops, we find that most shops tend to lean one way or the other. Most shops either are really good with the vinyls and the polyolefins like HDPE or say polypropylene. And when I say vinyls, we're talking PVC and CPVC. Or other shops, they like to work and weld the fluoropolymer. So we're talking like PVDF, ECTFE, FEP, some of those. And every thermoplastic has a different behavior. They have different hardnesses. They have different ranges that they have to be welded, and the ranges can vary quite widely. And the way they weld is much different as well. It's just like the difference between welding carbon steel and welding Hastelloy or titanium or something else. It takes a different skill set and a certain level of experience with every material, and the manufacturers need to be qualified on that same similar basis for thermoplastic linings as well. And then we always say, if you're evaluating manufacturers, ask for references, and really, particularly, we're talking today being kind of the COVID period we're going through. Everybody has had their challenges. Everybody has had to adapt. Every company and every manufacturer, we gain talent, we lose talent, we have our own trials and tribulations, and you need to audit them and go visit them and talk to them and see who's doing the work. Since, how long has their shop manager been there? Have they had any turnover? Those sort of things, just so you know that they have qualified people at every seat. So, and I've mentioned pipe stress analysis a couple of times now, and literally when I would say, particularly FRP and dual laminates, unless it's an ambient system where it's less than 100 degrees Fahrenheit and it's like a drain line or something like that, almost every process line, I would venture to say, should be analyzed with a formal pipe stress program. That's the only way that you're going to know that you have the right supports in the right places. I would venture to say that the best piping engineers out there that do non-metallics will lay out a system and analyze it, and it's probably 1 in 100 where they lay out the system the first time and push the button and analyze it and everything is perfect. There are always going to be stress points to work through, and the best people can't do it. So, your average engineer out there isn't going to be any different and probably not that good. So I would highly recommend that most of your non-metallic systems, and you should consider your thermoplastics as well, to be analyzed with a formal pipe stress program. If it's an important system, if it's a critical service, um, to analyze it is the best way to assure success in this, as far as the pipe support arrangement and layout goes. So it's an important part. It's not the only part, obviously, but it is definitely an important part that shouldn't be overlooked. And then pipe support. So I have some details here. So what I'm showing you here, you'll see the top two pictures where basically the pipe is sitting on the steel, and you can see the one on the right hand side where you see the light gray patch on the elbow there. That's one that's already failed. The image on the bottom is the result of setting the FRP pipe on the steel. So you see this crack that's going actually down the pipe, and you can actually see where the pipe has been worn on the steel from the thermal expansion and contraction. So the pipe is moving across the steel, and it gets abraded over time, and then it gets thin, and then basically, because you have a round pipe that's flexible on top of this hard flat surface, tends to create a pipe load, or a point load rather, that can crack the pipe in this manner. So it's important to have shields on most of your chemical process pipe as a minimum. Generally, our recommendation is we'll put shields on the pipe at a minimum up to about 10 inches in diameter. Beyond that, the pipe is much larger, greater loads, more flexibility. And really at that point, we start to recommend a full supported clamp at that point. But you definitely don't want, basically the supports are there to protect the pipe. The supports are lined with rubber generally in the clamp, so that even the supports themselves don't abrade the pipe in the clamp. So you definitely don't want to sit the pipe right on the steel. So some more discussions about FRP supports. So you can see the pictures at the top here. This is a large diameter duct. And you can see on the right-hand picture here where basically the pipe joint is actually sitting in the supports. You can see the overwrap is sitting in support. So it's obviously not going to fit well. And you can see that basically at this point, the support is creating a point load on the pipe because it's not really got the full surface contact. And if you look at the left-hand picture in the upper section, you can actually see where they actually split the support here, basically to make room for the pipe joint, because the pipe joints were so big and oversized for the clamps that they had to split the support to spread it out just to fit the pipe in. Definitely not an ideal situation at all. Ideally, in the design phase, you would like to see the engineers actually, identifying the locations of the supports, identifying the locations of the joints to where the joints did not interfere with the support. So you want the joints, a couple foot away, something like that. Doesn't have to be substantial, but just not to be in the same place, because you don't want to put a point load at a joint where you have a point of greatest concern, where generally the pipe's not going to fail. It's when we see leaks and failures, it's in the joints, it's in the T's, the elbows, the fittings, but to a great extent, it's in the joints. So we don't want to put the joints at a high stress point. And then the support at the bottom, you see is, it looks like a pretty good support, but it's rode off the steel. Well, this is what happens when you don't analyze a system and you have a lot of basically uncontrolled, unpredictable thermal expansion, where over time, the pipe moves back and forth, and then that support slowly inches off the steel. And now you have the support is actually just acting as an extra load on the pipe, and the pipe is either unsupported at that point at all, or it's sitting on the steel. Either way, it's pretty bad. So this is another case where you really want to look at pipe stress analysis. So, and talking about more lessons learned about materials, when we're looking at resin selection and thermoplastics, you know, in many cases, there's like most things, there's a good, better, and best, you know. But one point I want to make is when we're doing piping design, if you look at ASME, you know, best practices, we're always designing ideally for a 20+ year service life. You know, I've seen, you know, some manufacturers or some material suppliers will say, and you'll say, okay, well, I have this service, and this is the design conditions that I have, this is the chemistry, and they'll say, okay, well, it's a dual laminate, and here's the lining, and you know, what we find is, well, if we go to 3 different suppliers, I might get 3 different answers. One will say, you know, PVC, one will say polypropylene, another might say PVDF. And what I find is they all will work in that application, but one may be good for 7 years, one may be good for 10 years, and the other may be good for 20 years. So they'll all say it's good for it, but really, you know, when you look at the cost of replacing pipe, bringing a unit down in many cases, or at least a system, for probably not less than, you know, 5 to 10 days. When you look at lost production, to bring it down every 10 years, to rip it out, buy new pipe, put it in, it really doesn't make sense to buy that cheaper material. Really, ideally, you know, some of these applications are challenging, but as close as you can get to a 20-year service life is really how we would recommend to select resins, as well as our thermoplastic linings. And you know, I would always say, you know, beware of equals. If you want to look at alternative materials, you know, don't just take a letter of recommendation. Ask for data, ask for case histories. You know, look for proof of performance that it's a good choice, not just a recommendation. You know, in these days we're all accountable. You know, the level of data expectations is much higher. I think everybody should expect it, so it shouldn't be a problem to ask for that, and shouldn't be a problem to get it if they really support their products. So when it comes to fabrication, you know, certified bonders and welders are critical. If it were steel, you'd want to have a certified welder doing the work. You wouldn't allow a welder to work in a plant if he didn't have his, you know, current paper showing that he was certified for that material, certified for carbon steel or 316 stainless or Hastelloy or titanium or whatever it might be. You know, they would need to show papers that they're, you know, trained and current with that material. And the same is with FRP and with dual laminates as well. They do have certifications for these, and you should expect that. Even for something as simple as like thermoplastic solvent cement welding, you still want to have documentation that the guys doing the work in the field have been trained for those specific products, and they should be current. And one thing I wanted to mention specifically with thermoplastics is material compatibility. I guess CPVC is not CPVC, and what we find is that, you know, the base materials are same, but when they make tubes, when they make flat sheets, when they make welding rods for those, when they make fittings, there's a little bit of difference in the background chemistry to make it more moldable, to give it better mechanical properties, to give it more flexibility, whatever the concern may be. So that they do add some things. So it's important that particularly the welding rods that they use for those are compatible for that specific material. So say if it's CPVC specifically, that the welding rods come from the manufacturer or have been proven to be compatible with that specific manufacturer's sheet material or lining or fitting materials. To have one manufacturer's, you know, linings and another manufacturer's welding rods doesn't typically work out well. So you want to make sure that they're basically using compatible materials for welding that match the materials that the parent materials that they're welding to. I can't tell you how many times I've seen linings in dual laminate piping, as well as in process vessels, where the linings, you go in and inspect them and they look fine, and then you look closely and realize that all of the welds are gone because all the welds have dissolved from the chemistry because they weren't compatible with the sheet material. So it's important to specify this and then to check it in your inspections when you have your inspectors in the shop to examine the work being done. So wanted to talk about dual laminates a little bit, and specifically about fabrication. Typical dual laminate lining is typically something between 2.7 millimeters to 4 millimeters, maybe 5 millimeters max. So tolerances and gaps are important, just like welding up steel. So you want to make sure that the fit up is there, the tolerances are right. You want to make sure that every joint is spark tested to make sure there's no pinholes in the welding, just like if you were doing that with steel. And then specifically in dual laminate manufacturers shops, you want to make sure that they're doing the thermoplastic welding work in a clean room. I've seen sometimes when the thermoplastic welding is sharing the same space as the FRP welding is, where they're grinding and you see dust everywhere from the FRP. Well, if that gets into your thermoplastic welds, it can contaminate the welds, and you're going to have a pinhole show up there or created, from the first weld application. So you want to make sure that where they're doing the thermoplastic welding, that it's a clean space, that it's to some extent it's kind of environmentally controlled. And because it is a much more sophisticated product, you want to ideally have a third-party inspection, or if you've got an owner's inspector on your plant site, that you have a SME on your plant site, have them look at it as well. Inspection, because it is a much more complicated process and sophisticated material, we would highly recommend that you do inspection on that as well. And then one thing I wanted to mention specifically about post-cure in manufacturing is, when you have these more demanding surfaces like chlorine dioxide, HCl service, they are very aggressive materials, and we find that post-curing piping or vessels is important to extending the life and really meeting your expectation, getting your maximum service life out of it. If you post-cure products, and some of them require, chlorine is about as hard as it gets. You really need that. You must post-cure for a service like that. But even for HCl, we find that post-curing for these more severe services will generally give you something in the order of 3 to 5 more years. Is not unexpected, where we see premature failures or shorter lifespans. It's where maybe the post-cure wasn't done as completely as it should have been, or maybe it wasn't controlled as far as the temperature and the time as what it was specified. So some attention to detail needs to be paid in the post-cure process. And if you do that, you're definitely going to maximize your service life. So I've been in ASME for over 20 years probably, and regardless of the material, one of the biggest discussions that you hear almost every meeting is the discussion of torquing, flanges, and flange failures. Here's an example of a dual laminate system. This was, I believe, a polypropylene lining. You can see it's got a number of issues here, but there's a joint failure at the weld, where the lining actually meets the flange face. and that's where that blister is coming up. But then you see this crack around the, you know, like it's about ½ inch further out all the way around. This is a crack that basically comes to pass from poor torquing, and probably was not torqued at all. It was probably just bolted up and winched down, and there's probably not a torque wrench used on it. Generally, this is an indication that it was probably over torqued, and you can see basically it has compressed the thermoplastic lining on the flange face to a point to where it's created such compressive stresses that it actually cracked it over time. All of your dual laminate piping and all of your non-metallics in general should be torqued with a torque wrench, particularly lined pipe like dual laminates, lined steel pipe. Generally, once it's bolted up and torqued down, generally ideally before you put it into service, you want to go back and check those torques again, because the thermoplastic linings will settle, and you'll see the torques relieved a little bit. If you don't circle back and touch the torques up on those, you can see points where those flanges will end up leaking prematurely, and you'll have to go back and do them anyway. So if you do it in advance before you go into service, then that won't be a concern. But this is something that is typical across all materials, across all industries. Pretty much, flange bolting is definitely a challenge. So when we go into outages, you know, what we talk about is basically you want to be inspecting your equipment regularly. You want to develop a service life history so that each inspection you go into, you can look back at your documentation from the year before, or 2 years before, or 5 years before, and kind of see what the progression was. What were the issues last time we were in here? Is there anything that we need to be monitoring? Are there concerns that are starting to develop that we need to keep an eye on? You know, I want to point out that, you know, really documentation is critical for this. You can't have equipment in these services without really doing a regular inspection program and maintenance assessment program to make sure that you know what you have. If there's something is developing, that you know when it's time to replace it or when it's time to plan repairs. So that's always a critical point. And you know, I wanted to mention, you know, there are no silver bullets. There's lots of NDT out there, and they're helpful tools, but just by themselves, any one of them is not the silver bullet. And really, with your non-metallics, you're not going to have a full picture of your condition assessment without getting a visual inspection, particularly of the internals. If it were a vessel, you need to get inside the vessel with piping. If it's not so big that you can get inside it, you need to be taking a borescope, ideally through it, and so you can see what the condition of the pipes are, so that if there is something brewing, that you'll know about it before it surprises you. So to wrap it all up, you know, I guess my best recommendations are take the time to select the best materials. Obviously, it's always a challenge when you have budgets, but look at, you know, service life costs, you know, for the full service life, not just the capital expenses when you look at these, because the cost of replacement and rip out and to put new material in is substantial, and it'll outweigh any savings you have on the capital project side. If you have projects coming up, or even if you have, you know, if you're doing repairs just for maintenance, you know, have good specs, have specifications and procedures in place, so that when you have a manufacturer come in, that basically you're defining your expectations and what are the current best practices. And our practices do get better and better every year. So those specs do need to be updated from time to time. Ideally, I would say at least every 5 years or so. You know, look at the service life again, and you know, don't cut corners in the project. You know, you want to have your in-house SME or an outside third party doing your inspections making sure that everything is meeting expectations. Don't rely on somebody else to take care of that for you. Put your own eyes on it. Make sure that you know that it's the way that you want it, and you won't be surprised. So really, that's all I have today. You know, kind of what I've tried to reinforce here is basically you need to own it. You need to be diligent with your maintenance assessments, with selecting materials, and I think now we'll open it up to some questions. I do want to mention that you know, keep an eye out for our next webinar. We do these about once a month, so probably 1st of May or so first week or so we'll be putting together another one. So keep an eye out for that. And now I'll open it up for Tom to maybe offer some questions.
Okay, sounds good, Jeff. We do have a couple of questions here. The first question that came in early was, can you expand on the bonding between the thermoplastic layer and the FRP layers? How does that bond occur? Hey, Jeff, you may be muted. I can't hear you speaking if anyone else can. Well, everyone, we're having some trouble with the audio part of the presentation now as we're trying to switch back and forth. I apologize for that. Technical difficulties are an unfortunate part of some of these. So we did have a couple of good questions. I'll apologize that we won't be able to answer them.
Okay, Tom, I got unmuted.
Okay.
Can you hear me?
I hear you, Jeff.
Okay.
The floor is yours. The question was, can you expand on the bonding between thermoplastic and FRP layers?
Yeah, sorry about that, guys. I'm not quite sure what happened, but it seems like the more that we rely on this technical stuff, the more it kind of, I guess, breaks down on us from time to time. So with respect to bonding of dual laminates, you may recall the, let me see if I can go back to this slide with the dual laminates here. Okay, that's the one right there. So here's the range of thermoplastics that we have for bonding dual laminates. So you know, and looking at this range, generally speaking, you have two options here. You have basically some of them are chemically bonded and some of them are mechanically bonded. So if we look at like PVC or CPVC, possibly polypropylene, what we'll do with that is, so basically the pipe is made from the inside out. So you have a steel mandrel and you're going to lay down your lining material on top of that. It may be a tube or it may be a rolled sheet. and then we're going to bond the FRP to it. So if we're talking about like CPVC, we have a bonding resin, so that will apply to that, and it basically softens the outside of this CPVC and creates a bondable surface, and then we can wind the FRP directly on that. So it basically, that bonding resin ties it all together. If we look at our fluoropolymers as we go up to the top, say, an ECTFE or FEP, PVDF, most of those are going to have a bonding, basically a fabric on the backside of the thermoplastic, so that basically the fabric is basically impregnated. So 50% of it, more or less, is basically embedded into the backside of the thermoplastic lining, and 50% of that backing fabric, which it's kind of a woven mesh material. So it looking at it on the outside, looks like loops extending out of the thermoplastic. So basically you have these loops that are extended out, that when you wind your FRP on the back of it, basically it's getting embedded in the fiberglass on the other side. So that's what we call a mechanical bond, where you have this fabric backing, and the fabric backings could be anything from a polyester, like maybe a vinyl or something like that, to a glass fabric, to possibly Kevlar might be another option that you might see this backing material made of. And you would select that backing material based on the chemistry that you're going to have in the process. As I mentioned, thermoplastics, they do permeate. They do continue to permeate over time, some of them at different rates. But if it gets to that, that backing material, you don't want it to break down and lose your bond ideally. That's why you would kind of select the backing materials based on that. But generally speaking, you have chemical bonded for your kind of lower end vinyls and maybe your polyolefins. And then after that, when you get into fluoropolymers, because they are very slick and very hard to bond to, we do see the mechanical fabric backed bonding there.
Okay, sounds good, Jeff. We have another question about post-cure. And when do you specify a post-cure on a laminate, and what is the benefit of post-cure?
Well, post-cure would be something that we would specify in the specific application, in the service specific application. So if we know, say it's chlorine or HCl or something like that, we're going to say that post-cure is required. We're going to note something about a kind of slow heat up process, so many degrees, per minute or something like that, or per 10 minutes. And then we're going to note a hold period that might be related to the thickness of the product or the specific resin system. So it might say something of the order of, okay, post-cure at a sustained 180 degrees for 4 hours or something like that, with a ramp up and a ramp down after that, to assure that basically we have, the idea is that you want all of the molecules within the FRP to be cross-linked and to be fully bonded. So you want them all to be activated 100%, so that you get the best chemical resistance from the product that you're manufacturing. So that's kind of the idea. But you want to, it needs to be defined and required in the specs from the start. You can say, well, if under standard practices where you might not require a post-cure, you can say, well, if we don't achieve the bar calls that we set for this resin application, say it needs to be a 35 and we're only getting 30, well, obviously something's not quite coming along the way it should, and we need to post-cure to drive that cure through that product. So there are cases where we may not require it unless we see, a lower Barcol hardness or some other issue with the resin cure, and we want to make sure that it's cured all the way through to meet our expectations of hardness. That would be the other option. But generally, you want to say it's required or not, and it's only, you know, optional if you're not meeting some sort of hardness criteria or something along that line.
A follow-up question to that came in, Jeff. Do you need an oven to post-cure parts, or can you post-cure parts by hand using a heat gun?
No. I guess I guess to put it simply, it needs to be a controlled environment. It needs to be a closed environment. So if it's a pipe, if it's a vessel, it should be in an enclosed oven. So you want to have pour walls, ideally insulated. It needs to have thermocouples at, you know, ideally inside the pipe, on both ends of the pipe, to where you're, you know, measuring temperature, you know, every minute, every 30 seconds, every 10 minutes, something like that, where you're doing regular checks, and it's not a hand process. It should be a controlled process where it's regulated and measured, and it's definitely not something that you would be doing by hand. In the field, say you're joining pipe and you require a post cure on the pipe and the joints. You know, we might apply not a handgun, but we would apply, say, a heating blanket around the joint and require the joints to be post cured with a heating blanket for, you know, so many minutes or hours that way, to make sure that the joints are equally as cured as the pipe itself, as a field operation. But you know, a heat gun can help to kick it off, but it's at that point it's a very uncontrolled process. You really don't know how much you're getting through, or you might even burn the pipe if you put too much heat to it too quick and too focused the area. So heat guns really are not a good practice for post curing.
Okay. Good information. Thank you. We're running a little bit over time. Do you want to take another question?
I've got time. So
Okay.
I guess if anybody has to leave, I just want to say, you know, thanks for showing up, and look forward to having your questions next time. Otherwise, I'm here as long as you have questions.
Okay. This one I hesitate to toss to you because it may take a minute to answer. How do I know when I've reached the useful end of my service life?
Oh,
Right.
well, yeah, there's a lot of levels to that question. I guess if we're just talking straight FRP, I would say when you're inspecting and you see you're through the corrosion barrier, when you see that you're into the structure, and that you may, whether you're doing borescope or, you know, if we're in a tank, you know, if you see structural windings, if you see the pattern of woven roving, for example, with that cross hatch pattern, when you can see that clearly and there's no corrosion barrier on top of that, or you're down to, you know, the very last mat where you can tell the bale's not there, and generally you might have 2 or 3 mats, and you see that you're well, you know, into the corrosion barrier, and, you know, either the last mat is there, and generally you'll see spots where it is not there and you're into the structure. I would say at that point you're on borrowed time. You're definitely approaching the point where you're compromising the integrity of the structure of the pipe. So at that point, for an FRP pipe, I'd say it's time to replace it. When we're in dual laminates, it's a little different. And I guess let's back up even to like line steel. As I mentioned before, with like line steel, the thermoplastic lining is your only defense. When it gets to the steel, pretty much you're at a point where if it's something so corrosive that you need a lining, when it gets to that carbon steel or even stainless, it's generally a matter of weeks before you sort of see pinholes come through, and that pipe is toast, and you're going to have to react pretty quickly at that point if you've compromised the liner. With dual laminates, you do have that FRP structure, which also has a corrosion resistant, I guess, character to it. So it will help you to extend the life of the pipe. I mean, I guess I would say the school book practice, I'll say, is that when you go through the through that thermoplastic lining, at that point it's time to replace it. Okay, that's best practice. The reality is everybody's trying to squeeze every extra day, every extra year that they can out of the pipe, and you know, you have a pipe that has a design factor for pressure of 10. Generally, from a design standpoint, you know, looking at all influences, it's more like a 6. So once you go through that lining, you're into the structure, and you're compromising basically the design of the pipe. So you can, you know, buy a little bit of that. If it's goes from a 6 to a 4, that's not a big deal. But if you get below that, you're really, I mean, you're going to see leaks and failures start to show up. So, you know, if you want to go that route, I would say that you need to have a good inspector with a thorough evaluation assessment of all of the lining and systems. To really make those kind of choices, you need to have a, you know, good data and a good support group to kind of work in the margins, let's say. But you want to be very careful if you do that. It's not something I would say is necessarily that I would recommend broadly.
Sure. Okay, let's answer one more question before we let everyone go. Excuse me. How are the vastly different thermal expansion rates handled in the dual laminate piping systems when the thermoplastic liner is going to be significantly hotter typically than the fiberglass structural cage?
I don't know that it's a lot different. I mean, I can't say that I've measured it, but my experience would tell me that say you're at a surface that's say 90 degrees C on the inside of the surface. Well, that FRP, you know, structural component is probably going to see something maybe in the order of 70 degrees C on the inside. You know, there's going to be a temperature drop across the thermoplastic because it does have insulative properties, but it's not going to be substantially different. But you do have, as I already have shown, a significant difference in thermal expansion between the materials. And the key here is that bond that we talked about, whether it's the chemical bond or whether it is the mechanical bond with the fabric backing. If we have something close to 100% bond all the way through, generally we do not see the lining separate from the FRP structure. But that's the key, is to get that consistent bond throughout. But if we do that, it's very rare that we've seen a separation of the lining. So generally you have so much resistance in that and strength of the bond that's not really a concern. So even if we measure, you know, thermal expansion of the pipe itself, just with a coupon, say, and bringing it up to temperature, we don't see a substantial difference in a dual laminate versus a straight FRP, because to some extent FRP, because you have a high resin content in the corrosion barrier, you have a similar kind of effect. Not near as dramatic, obviously, as the thermoplastic, but it is a similar effect. But because we have good bonding practices and good execution, generally that's not a problem where you're going to see the lining separate from the FRP structure.
Okay. Sounds good. There are a couple other questions, but we'll let you return those personally with an email after this, and we'll let you close out the presentation. Thank you.
All right, great. Well, I just want to say, everybody, thanks for coming again, and I enjoyed talking with everybody today and appreciate all the questions. And just wanted to make sure, again, you will be seeing some feedback from us on this, as well as you'll be seeing notifications for upcoming webinars. We try to do these once a month, so keep an eye out, and probably within the next couple of weeks or so, you'll be seeing another announcement for next month's webinar. So thanks again and have a great day.